Hey there, how you doing? So when you dissect something, you start with the outside, with the skin, and then you cut it open and see what's inside. We're kind of doing the same thing with geometry. We started with the skin, the surface area of prisms and cylinders, and now we get our geometric scalpel out and find out what's inside. We're doing volume of prisms and cylinders today. So jumping into BJU chapter 9.4, let's get into it. Area, remember, is the number of square units that you need to cover the surface of an object. Volume now is the number of cubic units you need to fill an interior completely. So with surface area, we're looking at things like square centimeters. With volume, we're looking at things like cubic centimeters. Okay, so last couple of sections, your answers all had some kind of unit squared. Now you're going to have answers that have some kind of unit to the third power, okay, because we're talking about cubic units. Oh, let's go backwards. This leads us to the first theorem, that every solid has a volume given by a unique positive real number. Every solid thing, hey look, it's my coffee cup again, I used this last time. Every solid object like this one has a positive real number that you can reflect as its volume. Volume in cubic inches, volume in cubic centimeters, volume in cubic meters, although it would be a very small fraction of one. You can represent any volume with a real positive number. So this rectangular object here has a volume that we could quite easily calculate. Now I haven't given you the theorem yet to be able to calculate this, but I bet just given your amazing God-given intellect, you can look at this and figure out how many cubes there are in this rectangular prism. I'll give you just a second. How many are there? If you said 72, you're right. How did you get to 72? Well, you probably thought, oh, it's 4 by 3 that gives me the area of the base, and then I bet it's just times 6. 4 times 3 is 12, times 6 is 72. And you'd be right. Look, you just figured out your own geometry theorem. Praise the Lord for your brain. Let's move on. Theorem 9.4.2 is this, but you already know that because you figured it out. Here we are. The volume of a rectangular prism is the product of its length, width, and height. Volume equals LWH, length times width times height. Okay, that's why you have cubic units, because it's 3 things getting multiplied together. If the thing that you're multiplying all together happens to have every dimension the same, it's a cube, right? Like a sugar cube or like a die. If it's the same size in all 3 dimensions, then it's just the side length or the edge length cubed. That'll give you the volume, so that's pretty easy. What's the volume of a cube whose side length is 2 inches? 2 to the third power, 8. Okay, what's the size of a cube whose edge length is 3 inches? 3 to the third power, 27. So you can think about a cube just as a really easy rectangle. What happens if the prism is not a rectangle or a cube? What happens if the prism has a weird polygon shape on the bottom? Well, you just need to get the area of that polygon and then multiply it by its height. Area of the base times its height. Okay, so the volume of a prism is the product of its height and the area of its base. So we'll do some examples with that. Also, if I have a volume of one object and I add another object to it, then I can tell you that the volume of the union is the volume of the 2 objects separately that have been joined together. So coffee cup to the rescue and water bottle, because you should always drink more water than coffee. Okay, there you go. That little biology tip is free. If I want to know what is the volume of these 2 objects together, I could get the volume of the coffee cup, the volume of the water bottle, and I could add them together, and that would be the volume of this object, right? This object, which is a whole lot of fluid that will eventually be inside me. There you go. So the volume of a union of 2 objects is their volume independently added together. Here's a really quick, easy idea. If you have 2 congruent solids, then their volumes are congruent as well. The volumes are the same. So my wife has a coffee cup just like this. Boy, I like this coffee cup. Can you tell? My wife has a coffee cup just like this, but hers is red. They are congruent. They're the same way in every size. Same size in every way. The volume of mine is exactly the same as the volume of hers. And so congruent solids have equal volume. This one's interesting. If you have a prism and you pass a plane parallel to the base of the prism, anywhere through the prism, you will have a polygon that is congruent to the base. So here's my have I shown you my coffee cup? Coffee cup sitting on a flat surface. If I take a plane and I pass it through this cup, as long as it is parallel to the base, then I will have a shape that is congruent to the base. So this is a polygon, a circle, not a polygon. The same idea works, right? This is a circle of a certain diameter. This is a circle of a certain diameter. This is a circle of a certain diameter. And if this were a perfect cylinder, which is kind of wavy, but anyway, if it were a perfect cylinder, no matter where I slice it, no matter where I pass that plane, as long as it's parallel to the base, I get a congruent figure. Here's just a picture that will help us with a couple of the different concepts we've just explored. So the volume of this prism is length times width times height, and that will give you the volume of this prism. And it doesn't matter if it's right or oblique. Right means straight up and down, oblique means kind of slanty, okay? These two prisms, as long as they have the same height, will have the same volume. Now in your brain you're going to be like, but wait a minute, if I push this thing over, it's going to get slightly smaller inside. See, that's not what's happening, because if you push this thing over, h also gets a little bit smaller. We're talking about h being the same, so you'd have to like pull up and then slide over for h to stay the same, in which case the volume stays the same. Okay, and here we have a plane passing through this prism that is parallel to the base, and it will be congruent to the base. Okay, and it doesn't matter if it's right or oblique. An oblique prism will also have a congruent polygon to the base. All right, hope that helps. This one is a little bit different. So in that last picture, the prisms were regular prisms, square prisms, rectangular prisms, easily identifiable as being congruent to each other given base area and height, things like that. What happens if it's a wonky solid? If it's a wonky solid, that's not a regular prism. It's some kind of thing, right? Well, the way I can see if these two things are congruent is if I slice it in the same plane at the same height from the base in each of these two wonky solids, and I wind up with polygons of equal area, then, and if I do that in multiple places, and no matter where I pass my plane, I get two shapes of equal area, then I do in fact have two congruent wonky polyhedra or prisms. Okay, so that's Cavalieri's principle. Cavalieri, wonky already. Let's throw an example at you. Here I have a hexagonal prism. All they've told me is a side edge length and the height. They did not tell me the apothem, but that's no sweat, right? We can do this. Here I have an edge length of 8, and that means that this is also 8, which means that half of this is 4. And this is a 30, 60, 90 degree triangle right in here. Don't know why they didn't draw that to help your brain. Remember also that in a hexagon, on a regular hexagon, the radius is equal to the edge length. And so the radius here is also 8. And so I have a 30, 60, 90 degree triangle. This is 4. The hypotenuse is 8. And what's this long leg? Well, in a 30, 60, 90, the long leg is radical 3 times the short leg. Remember that? So 4 radical 3 is my apothem. That's what this would be right here. And the formula for the hexagon is 1/2 times apothem times perimeter, 1/2 times 4 radical 3 times 48. Half of 4 is 2. 2 times radical 3 times 48. 2 times 4 is 90. Sorry, 2 times 4. 2 times 48 is 96. 96 radical 3 square centimeters is the area of that hexagon. Now I have to multiply that by the height, by 14 radical 3. Well, here's a cool thing. This is radical 3, and this is radical 3. What happens when two radical 3's get multiplied together? Square root of 3 times the square root of 3, you get 3. That was pretty simple. So all we've got to really do is 96 radical 3 times 14 radical 3. 96 times 14 is 1,344 times 3, because the radical 3 times radical 3 is just 3. So the answer is 4,032 cubic centimeters. Let me know if you have any questions about that. We can work through some more tomorrow. Just like a prism, the area of, the volume of a cylinder is the base area times the height. So you've got a circular base, you got to use the pi r squared for this one instead of height times width or something like that. But once you get the circular area, you just multiply that by the height. And that works for right cylinders and for oblique slanty cylinders like the Tower of Pisa as well. Just to give this to you in theorem form, what I just told you is that the volume of a cylinder is the base area times the height, and for circles you have to use pi r squared for the base area. So the volume of a cylinder is pi r squared h. There you have it, ladies and gentlemen. Theorem 9.44. Give it a round of applause. And they now want to know how many cubic inches of sand do you need to fill this cylinder, and it is a 5-inch cylinder radius and 12-inch cylinder height. Pi r squared h, pi times 5 squared times 12, 5 squared is 25, 25 times 12 is 300. 300 pi cubic inches would be a fine answer. If you wanted to go all the way to the decimal, that's 942.5 cubic inches. That's also acceptable. I'll take either of those on a quiz. Okay. Last example. How high would I have to fill a corn silo if the corn silo has a diameter is not a radius, of 20 feet, and I've got 22,000 cubic feet of corn. It was a good year on the corn farm this year. I want to fill my corn silo. How high up is it going to go? 20-foot diameter, 10-foot radius, right? So V equals pi r squared h. My V is now a known value, 22,000 cubic feet, equals pi 10 squared h. 10 squared is 100. So now I need to divide 22,000 by 10 pi, and I can just whack off 2 zeros. 220 divided by pi is 70 approximately, 69.9 yada yada yada. 70 approximately feet. It's a 70-foot tall silo. That was a good year on the corn farm. Alrighty, speaking of a good year, we're having a great time with geometry, aren't we? That's it. Let me know if you have any questions, and put them in the comments field below, and I'll get to them as quickly as I can. Otherwise, God bless you. Jesus loves you, and so do I. Have a good night.